Hello, I'm Damla Senol Cali. Today I will be presenting our work, GenASM, a high-performance, low-power approximate string matching acceleration framework for genome sequence analysis. Genome sequencing, which enables us to determine the DNA sequence of an organism, plays a pivotal role in areas such as personalized medicine, outbreak tracing like COVID-19, and the understanding of evolution. Modern genome sequencing machines extract small randomized fragments of the original DNA sequence, which we call reads. State-of-the-art sequencing machines produce either short reads or long reads. Read mapping is the first key step in genome sequence analysis, where we align each read to one or more possible locations within the reference genome and find the matches and differences between the read and the reference genome segment at that location. Multiple steps of read mapping must account for the sequencing errors and for the differences caused by genetic variations. As a result, read mapping must perform approximate string matching or ASM. However, it is currently bottlenecked by the computational power and memory bandwidth limitations of existing systems. Our goal in this work is to design a fast and flexible framework for both short and long reads, which can accelerate multiple steps of genome sequence analysis. To this end, we propose GenASM, and we base GenASM on BiTAP, an ASM algorithm that uses only fast and simple bitwise operations, making it amenable to efficient hardware acceleration. To our knowledge, GenASM is the first work that enhances and accelerates BiTAP, and also it is the first ASM acceleration framework for genome sequence analysis. We modified BiTAP to support long reads and to enable parallelization. We also developed a novel BiTAP-compatible algorithm for traceback, and we co-designed specialized low-power and area-efficient hardware for both algorithms. Our co-designed hardware consists of two components. First, Jenason DC, which provides hardware support to efficiently execute our modified BiTAP algorithm to perform distance calculation. And second, Jenason TB, which provides hardware support to efficiently execute our novel traceback algorithm to find the optimal alignment. GenASM also has two types of SRAM buffers, DC SRAM and TB SRAMs. Our specialized compute units and on-chip SRAMs help us to match the rate of computation with memory capacity and memory bandwidth, achieve high performance and power efficiency, and also scale linearly in performance with the number of parallel compute units that we add to the system. We implement GenASM DC as a linear cyclic systolic array-based accelerator using small and very simple logic components. This design helps us to maximize parallelism and minimize memory bandwidth and memory footprint. So processing core is the basic compute component which computes the intermediate bit vectors. And when we add the flip-flop based storage logic around the processing core, we define a processing element or PE. Multiple PEs are concatenated to define a processing block. We also have DC SRAM, which stores the reference text, the pattern bit masks for the query read, and the intermediate data generated from PEs. And we also have TB SRAMs, which store the intermediate bit vectors generated by each PE of GenASM DC for later use by GenASM TB. We implement GenASM TB hardware using very simple logic, which first reads the bit vectors from one of the TB SRAMs using the computed address, then performs the required bitwise comparisons to find the traceback output for the current position, and finally computes the next TB SRAM address to read the new set of bit vectors. After GenASM TB finds the complete traceback output, it writes this output to main memory and completes its execution. We synthesize our DC and TB accelerator data paths with a typical 28 nanometer low power process, and when both accelerators operate at 1 gigahertz, we find that for 32 GenASM accelerators, one for each HMC volt, total area overhead is 10.69 millimeters square, and total power consumption is 3.23 watts. We observe that both area and power consumption of GenASM at a single volt is around 1% of the area and power consumption of a single Xeon CPU core. So, GenASM has low area and power overheads. GenASM is flexible and can be used for a number of use cases. In this work, we evaluate 3 of them in detail, and 2 of them are from the read mapping pipeline. pre-alignment filtering, and read alignment. So read alignment is the most time-consuming step of read mapping that we align each read to all of its candidate reference regions and then find the optimal alignment. In pre-alignment filtering for short reads, we aim to quickly identify and filter out the unlikely candidate reference regions of each read by approximating the edit distance between them and filtering out if it is above a threshold. And our third use case is edit distance calculation, which is one of the fundamental operations in genomics that measures the similarity or distance between any given sequences. In our paper, we also briefly discuss several other use cases, such as generic text search. We find that for all the three use cases, GenASM is significantly more efficient in terms of both speed and power consumption than state-of-the-art software and hardware baselines. Thank you.